Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online structural geology NPTEL course. We are at our lecture number 18 and this week we are learning planar fabrics and linear fabrics. So, we are on lecture number 2 in this week. In the previous lecture, which is lecture number 17, we learned the very basic and generic classifications of planar fabrics. We also learned how to differentiate primary and secondary fabrics. In the primary fabrics, we mostly considered the sedimentary layers, and secondary fabrics we considered deformation induced fabrics. So, in this lecture we will mostly cover these following topics. So, first we will do a morphological classification of planar fabrics, that means the way they appear, it is not their generic nature, and then we will actually look for some very special attributes of planar fabrics which are associated with different structural styles, particularly folds, and they have some special names as well. So, we learn one after another. We will also try to figure out what is their mechanism of formations, and at the very end of this lecture we will particularly focus on the origin and micromechanics of planar fabrics. So, when we talk about the morphological classifications of foliations or secondary foliations in particular, a series of morphological features are considered, and what are these specially are listed here, mostly 5 characters we consider. So, first one is the spacing between the planes or planar domains, that how closely they are spaced and what is in within the space. We will look at it soon. Then shape of the planes, whether it is rough, smooth, wiggly, etc., etc. Then we will also consider spatial relationship between the planes, that means whether these planes are parallel to each other, anastomosing to each other, whether these are conjugate, cross cutting, and so on. We also look whether what is the characteristics of the boundaries of the planar domains, whether these boundaries of these foliations are gradational, sharp, discrete, etc., etc., and essentially finally look at the fabric of the rock between the foliation planes, that means whether this is planar or folded and so on. Now, one thing is very important to understand at this point, that all these morphologies that we talked about, whether be it spacing, shape, their spatial relationship, characteristics of the boundaries, fabric of the rocks, etc., etc., all these are functions of the metamorphic grade of the deformation or metamorphic grade of the rock. What was the PT conditions, what was the heating and cooling history, what was the fluid activities, etc., etc. We will look at it later, but the spacing, shape, spatial relationship, characteristic of the boundaries, fabric of the rock, etc., etc., all these do vary greatly with the metamorphic grade of the rock. So, here is the table that classifies the secondary foliations. So, if we consider secondary foliation at one end, then we can classify it in 2 broad domain. One is spaced foliation and another is continuous foliation. The spaced foliation is further subdivided in 3 different categories. The first one is compositional foliation or compositional spaced foliation, then disjunctive foliation and crenulation foliation or crenulation cleavage. Within the continuous domain, we have fine grained continuous foliation and coarse grained continuous foliations, or the fine foliation or coarse foliation based on their spacings and so on. Now, within the compositional cleavage or compositional foliation, we have 2 subclasses, diffused or banded. So, that means whether the boundaries are diffused or sharply banded. Then within the disjunctive, we have stylolites, anastomosing, rough and smooth. Within the crenulation we have zonal and discrete, and then in the domain of continuous cleavage we have two classes we discussed, fine and coarse. Within the fine we have micro crenulation, micro disjunctive and micro discontinuous, these three, and within the coarse foliation we have mineral grains and discretes. So, we will not really look at the last column here, but we certainly talk about spaced foliation, continuous foliation, and within the spaced we talk about compositional disjunctive crenulation, and then within the continuous we very briefly discuss the fine and coarse grained foliations. So, let us have a look what do we mean by spacing in the foliations and how do we characterize them. As you can see in these illustrations that from this end, from your left side to the right side of the screen, you see a series of lines are drawn, and on the right side the spacings between the lines from the left side have continuously decreased. Now, if we try to put them in a scaled form, so if I consider here the spacing is about 0.1 millimeter, here is 1 millimeter, here is 10 millimeter, here is 100 millimeter, that means close to 10 centimeters, and here is 1000 millimeters, that means 1 meter. So, this is in log scale. So, if the spacings between the two cleavages or two deformed domains in the foliated rock is extremely close or is close to 0.1 millimeter or less, then we define it as slaty cleavage. That means you cannot distinguish the space between the two foliations or two layers of foliations. However, if the spaces increases or however if the spaces increase, then we arrive to strong foliation where the spacing is around 1 millimeter, then we arrive to moderate where the spacing is about 10 millimeter, then weak, and then here we arrive to isolated stylolite, which we actually do not consider as foliation, because if you remember in the first lecture we decided that whatever is more than 10 centimeters, the spacings between the two foliations, if it is more than 10 centimeters, particularly for secondary foliations, we do not consider it as a foliation. Now, there is also one important aspect in considering this slaty, strong, moderate and weak cleavage, because in the field not necessarily you are carrying the scale or you would be measure. So, you generally look at by your eyes, but when you take this rock in the laboratory, the foliation you considered in the field as slaty cleavage or strong cleavage, when you look at under microscope you might find that this is actually a spaced cleavage. So, this is also very scale dependent, though I have tried to give you some sort of scaling ideas of what is the foliation. So, in summary, if you do not have much space between the two foliations, then we assign the name as continuous cleavage, and if we have spaces between them that we can recognize, be in field or be under microscope, we call it spaced cleavage. Now, based on whether this is continuous or spaced, we classify it in a different way. So, the two nomenclatures come in the picture, one is cleavage domain and another is microlithon. What are these two? These two are very important in the context of the spaced and continuous foliations or cleavage. Now, cleavage domains are generally assigned to the fact that it describes the concentrated zones of fabrics which actually defines the cleavage or the foliation. So, if I see that a rock is foliated, so what is defining the foliation or the zone which is defining the foliation is the cleavage domain, and what is in between two adjacent cleavage domains is microlithon. So, in other way we can define now the continuous cleavage, which is this one. I have made an illustration for you. So, if you do not find a space between the cleavage domains. So, in this case all these striations like thing, these lines here, you see these the traces of the foliation on this screen. There is no space in between, or at least these spaces are not very well defined or visible. So, therefore, we assign it as continuous cleavage. That means a cleavage which has only cleavage domains, but not microlithons at the scale we are looking at, we call it continuous cleavage. Disjunctive cleavage on the other hand is where you have microlithons in between the two adjacent cleavage domains. For example, in this image, the second one, what we see here again, this is a trace of the foliations on the screen we are looking at. What we see here, these grayish lines are your cleavage domains, and in between the cleavage domains. So, if I consider this area, so what I am drawing with the red line is the cleavage domain, and in this case these are anastomosing, and what is in between within the two cleavage domains here and here, these two are the microlithons. So, in this entire illustration you have alternating microlithons and cleavage domains in anastomosing manner. In the third image, what we see here, that cleavage or foliations are defined by these lines which are the traces of this very closely spaced microfolds or microcurvatures. Now, we will see later that these particular domains which are actually defining this domain and this domain, which are actually defining the foliated nature of the rock. We will see later that these are mostly defined by the concentration of phyllosilicates, mica and so on. And what we have in between this and this is the exposition or disposition of this microfolds. Now, what is the difference between then this image and this image, the second one and the third one? In the second one, we see that these microlithons are actually isotropic, they do not have any fabric within them. However, here this is the microlithon domain between the two cleavage domains, and we have a very consistent fabric within them. So, a disjunctive cleavage is, if we do not have fabric within the microlithons, then we call it disjunctive cleavage. I repeat, if the microlithons are devoid of any fabric, then this is disjunctive cleavage. On the other hand, if the microlithons have some fabrics, then these are crenulation cleavage. We will see some actual images soon. So, I believe now it is clear what is continuous cleavage, what is disjunctive cleavage, and what is crenulation cleavage. Now, we will look at a series of photographs. So, first we start with continuous cleavage in the field scale. The first image you see on the left side, this is shell, and as the title suggests that this is slaty cleavage. So, you can actually figure out immediately that this is your secondary foliation based on the appearance of this, and they are continuous because you do not see any space between this foliation. They are very much continuous foliation. In the second image as well, you may figure out that okay, these maybe there are some spaces between these two, but if you look closely, then you will figure out that even within this mica schist, which is a photograph from the again the Chaibasa formation, actually these are like books, the sheet of the books or the pages of the books. It's very closely, very densely spaced. So, you do not find the thickness of the pages by, or you do not figure out the thickness of the pages by your naked eyes. So, these are examples of continuous cleavage. As you can see here, I also give you a tip continuous cleavages are generally the first cleavage that you form after the deformation. So, if I have a sedimentary rock and I deform it, or even an igneous rock, the first foliation that forms out of deformation is generally continuous in nature. The next generation foliations are mostly spaced cleavage, where the form surface is the continuous foliation itself. Now, this is an optical photomicrograph. What you can see here, the entire width of this image is 1.8 millimeter. What we see here again, this is also slaty cleavage, and this is also in a slate, that is why the name came from slaty cleavage. And you also can see that you hardly can figure out the space between the two foliation planes or the traces of these lines, where you do not find any space between them. It's very much continuous in this side, and they are very closely spaced. So, the sense of the foliation is certainly there, but you can't figure out the spaces between them. So, this is a continuous cleavage in micro scale. So, we have seen continuous cleavage in field scale in the previous slide, and they more or less appear in a very similar way in the micro scale, only the scales are different, but characteristics are very much similar. Let us have a look to the disjunctive cleavage in the field scale. What we see here, these are some sort of solution seams. So, clearly these are your cleavage domains. They are anastomosing in nature, as you have seen in the illustration in few slides back. Few are strong, few are weak. But what is important, as we have defined disjunctive cleavages, that within these two cleavage domains, if I consider this one and this one, the material here is very much isotropic in terms of their fabric. The fabric is of 0th dimension. So, there is no fabric in between, just this anastomosing cleavage domains we see. So, this is disjunctive cleavage in the field scale. Do we see it in the micro scale? The answer is yes. So, here is one of this microscopic image under cross polarized light, and you see here that the cleavage domain here is quite broad, where we see the concentration of biotite, this greenish mineral, and in between. So, this is cleavage domain, and this is as well. And in between what we have is the microlithon. Now, the microlithon we see there is virtually no fabric, and this microlithon, at least in this optical image, we see it is mostly composed of quartz, whether this is with biotite rich minerals, phyllosilicates. Sometimes this kind of structures where you have bands in micro scale or in field scale, alternating bands of phyllosilicate rich layers and quartzo-feldspathic layers, again phyllosilicate layers, then quartzo-feldspathic layers, and so on. This is also sometimes known as PQ foliation or PQ structure, whether so this is known as P, whether P stands for pellitic, and these are known as Q, whether Q stands for quartz, and together we call them sometimes PQ foliation or PQ structure. So, this is something new for you, but again I repeat what we are learning here, that we have cleavage domains, series of cleavage domains, and in between we have microlithons, and microlithons here in this image have no fabric. So, we saw this in the field scale, and now we have seen it in the micro scale Again, the mechanisms are very similar, only the scales are different. Now, we will see granulation cleavage in the field scale. This image is again from the Chaibasa formation, and you may figure out a little bit difficult to comprehend that where is the granulation cleavage. I hope I can convince you there. Now, first let us figure out where is the foliation here. Now, as I said that continuous cleavage is generally the first order foliation, the first foliation it generates, and then comes the spaced cleavages and so on. So, granulation cleavage in most of the cases are the second generation cleavage. So, this is they develop in response to the second stage of the deformation. So, if we see here, we clearly can figure out that we have a foliation going on like this, and this is your right, this is your continuous foliation. Now, the question is, where is the granulation cleavage then? Now, if you look carefully, you may see that a fabric is being developed like this, and this is how you identify fabric in the field. You come closer, you go a little further, you look at it, and then you use the shadow, and then you try to sense what sort of fabrics I can figure out from this rock. I believe now you are convinced that this red one is your continuous foliation, no issues, but there is some sort of spaced fabric which is there defined by this blue lines. Now, if I wipe this one and I try to figure out what is there in between the space fabric, again this image is little blurred, but I try to convince you, but you will be convinced when you look at in the next image. So, what we see here, if we try to look at that, if I consider for example this layer and this layer and this layer and this layer and so on, we clearly see here that these continuous foliations, they are getting some sort of folded and then coming here like this. We also can see it here. And these particular orientation is defining the cleavage. So, therefore, this we can consider as granulation cleavage, because I have cleavage domains, and at the same time what I see here that within the microlithons I have some sort of fabric. The image you see at the background of this lecture is actually a thin section of this rock, and I believe you are now convinced that this is a granulation cleavage. So, here is an example of granulation cleavage again from the micro scale. This is 7 millimeter is the width of this image, and you clearly see that these are your cleavage domains, and within the cleavage domains, if I consider here and here, we certainly have some sort of fabrics going on which are defining your cleavage. And because we have in between the two cleavage domains microlithons, and microlithons have some fabrics, so therefore, this is granulation cleavage. Let us have a look to another example. So, what we see here, these are your again muscovite biotite rich zone, and these are your cleavage domains. So, these are your cleavage domain, this is also cleavage domain, and this is also cleavage domain, and in between you have microlithon and so on. Now, how are these microlithons? Yes, we have a fabric here within this microlithon. and therefore, this is a crenulation cleavage. So, if we try to figure out now that what is the relationship between the metamorphism and the fabric development, I have summarized a table here which is very much comprehensive for you. So, on the left side we have the rock names, and we started with slate, which is a very low grade metamorphic rock. Then we slowly approach to phyllite, schist, gneiss and migmatite. So, from top to bottom the grade of metamorphism has increased. Then how do they look like under thin sections is defined in the second column. You can see here slate is defined by very, very fine grains. So, the grain size is here, relative grain size, and it is generally produce and this generally produces excellent cleavage. So, the comments are here, excellent rock cleavage, and we have learned that this must be the continuous cleavage. Then in phyllite the grain size is fine, and we have foliation that develops like this. In schist, this is medium to coarse grain rock, mostly micaceous minerals are present, and we see some sort of scaly foliations as we see here this way. Then gneiss is again medium to coarse grain rock or sometimes pretty coarse grain rock, and here we mostly see compositional bandings due to segregation of minerals. And if this segregation of minerals happen in a very, very extensive way, then what we form is migmatite due to the partial melting of the gneiss or granitic rocks. So, here we see alternate dark and lighter color bands. So, this is essentially a banded rock, but here you do not see the primary foliations at all. So, it is mostly secondary foliations, and these banded rocks are characterized by zones of light and dark colored minerals. So, they are concentrated and segregated. The light colored areas are known as leucosome, you know it from your metamorphism classes, and the dark colored zones or layers are known as melanosomes. So, this is a very comprehensive table to guide you that what sort of foliations or what sort of secondary cleavages you would expect with the degree of metamorphism, what would be the grain size, what is their parent rock, and so on. Now, there are some other type of foliations where we look at it after the basic classifications. These are very typical, but they are very important to identify and go with. The first one we take over is transposed foliation. Now, transposed layering is something which is defined by parts of a pre-deformation surface. So, it could be bedding or older foliation which are rotated independently into a new orientation. After intense deformation of all these parts become some sort of subparallel. What we see here in this illustration, I took it from the lectures of Professor John Pierre Bourd. So, this was the initial orientation of the bedding plane, and this is the orientation of the foliation plane or cleavage plane, and they are perpendicular to each other. Now, if the beddings were parallel to this, then these beddings actually, so I had initial bedding like this, and because of compression, so this was my primary foliation layer, because of compression it can fold very, very tightly. And then you develop your secondary foliation in this manner. We will learn soon that these are axial planar cleavages. So, this is exactly what we see here. These are tightly folded, and on this side if we cut it along the bedding planes, we see that the traces of this are something like this. So, they become so tight, sometimes they are isolated, and they actually also are parallel to the foliation. So, they transpose themselves to the foliation plane, to the secondary foliation planes, and these are known as transposed foliation. So, here are some examples, as you can see here. So, it mostly happens when the fold is very tight, and there are many ways you can recognize this transposition or transposed foliation. So, one is this foliation parallel to the bedding or secondary layers. Second one is isolated intrafolial fold hinges. We learn about this term during our fold lectures. Then isolated boudins of competed layers, and of course, extreme flattening of strain markers. So, if you have a circular strain marker and that got extremely flattened, then it becomes like a line, like a plane, and therefore, like a line in a section and plane on the surface. So, what we see in this image, the first one, you clearly can identify that this is your foliation plane. And if you carefully look at, you will see that some tight folding is going on this way, and I do not know where did it go, but yes, here there might be some extremely tight folding. So, these are almost subparallel to the foliation plane. In the second image, if we try to look at, again we have the foliation plane, as you can figure out, is vertical in this case, and you can clearly figure out this white layer which gave you the fold like this, and so on here as well. This is very interesting. And so on, this probably went up and then probably it has a rotation and came back somewhere like this. So, this is extremely complex, but you can see that this is almost aligned subparallel to the foliation. And here as well we can see this is little difficult to figure out, but we see here the foliation is like this, and this is a continuous cleavage or continuous foliation, and we see some rootless sedimentary layers here, then something here, and actually you can see these are very, very fine. So, these are again also aligned with the secondary continuous foliations. So, sometimes these things did happen due to pressure solutions and the transposition, and these what you see here or what I have drawn here, these are some folded lenses or sandstone lenses which got folded, and now they are aligned with the foliation planes. Now, we will look at, after the transposed foliations, the most important part of the studying foliation is the foliation associated with folds. Now, I have drawn a few sketches, and you have also seen that folds are associated with mostly foliations or vice versa. Now, experiments and detailed case studies of natural folds show that after about 30% of the bulk shortening accommodated at the layer scale, that means you are shortening the layer by 30%, then it changes the grain orientation, and then it triggers the appearance of foliation. So, you need at least close to 35% or more bulk shortening to develop the fold induced foliation. Now, these foliations which are associated with the fold are known as axial planar foliation or axial planar cleavage, that develops parallel to the axial planes, or in other words, this is the first time we are stating it, that xy plane of the strain ellipsoid of the folds, and both are usually perpendicular to the maximum compressive stress at the time of deformation. So, what we mean by this, that if I have a layer like this and we deform it this way, then if the layer gets folded like this, then clearly if I had a sphere here, then sphere would turn to an ellipsoid. At least in this case I can consider that this is my x direction, this is my y direction, and because this is the shortening direction, so this is the z direction. So, axial planar cleavage would form in this manner, or there will be a series of lines. So, you clearly see this plane, this axial planar cleavage plane, which I am now sort of making some hatches. This plane is actually parallel to the xy plane of the strain ellipsoid. Now, whether this is x direction or this one is the x direction, we would figure it out later, but in this case, yes, as I have drawn, this is the x direction, but essentially this is your z direction and this is your xy plane. So, axial planar foliation, most of the cases are parallel to the xy plane of the local strain ellipsoid, and both axial planar cleavage and the xy plane are generally perpendicular to the maximum compressive stress at the time of deformation. Now, when we talk about this axial planar foliations, it has many applications, but today we will look at, or many structural features, but today we will look at mostly three aspects of this. One is cleavage or foliation refraction, another is cleavage or foliation fan, and another is transaction of cleavage and foliation. Now, refractions and fans are more or less a very similar process, but we see them in a different scale, and transaction is a different process. Now, we will look at all these three in detail in this lecture, but before that let us talk more about axial planar foliation for a while. The main structural reason of axial plane foliation is the parallel or subparallel alignment of platy minerals. So, this we probably have understood right now. Now, foliations are systematically associated with tectonic deformation and are mostly common in all grades of metamorphic rocks, and the mechanism which is believed to be behind the development of foliation is the ductile flattening. Now, what we see here in this illustration, that this pink layer is a stiff layer and this yellow layer is the soft layer, and if we deform it this way, this has a series of micaceous minerals like we have seen, like here we see these black lines here, and if we shorten it, then we see the horizontal trace foliations where all these little black minerals, they try to align along the extension direction of this deformation. So, if shortening is this way, then they try to align in this way, and then we develop a foliation which is known as axial planar foliation. We will have a look on some photographs. The first one, as you can see, these are your primary foliation, okay, and the primary foliations are curved, so they got folded, and we certainly see a series of continuous cleavage developed here. Okay. So, these are your axial planar foliation. Okay. The next one is one of my favorite photographs. I took it from British Geological Survey web page. So, you see these are your traces of the bedding planes or primary foliation you can think of. It has some sublamina inside and so on, but so nicely you see the axial planar foliations have formed in this image. And it is very similar mechanism, the rocks are different, but whenever we buckle a rock or buckle some layers, competent incompetent layers, we generally form a foliation, and these are known as axial planar foliation. Now, let us talk about these three terms that we have just talked about: cleavage diffraction, cleavage fanning, and transaction of the cleavage. We will first take over cleavage diffraction. Now, cleavage diffraction is something very interesting that do happen particularly when you have folding in multi layers, where the two layers or 2-3 different layers have different grain sizes or different compositions. So, that means their rheology is different. Now, if that happens, then this change of angular relation and that changes the angular relationship between the foliation and the bedding across the lithological boundaries, and therefore, we do not see the foliations are very straight. So, they go in a zigzag manner, and this is known as foliation or cleavage diffraction. And this diffraction mostly occurs because of the viscosity contrast along alternating layers, which produces the differential strain at different places in different ways. So, if I try to summarize it, say for example, I have a homogeneous body, I have a circle, we have learnt all about it, and I deform it by both compression and shear, then I know that this would take a shape like this. I am sorry, this should get a little shortened as well. Okay, and this ellipse would, this circle would take a shape of this ellipse. But if I have two different layers, say this one is competent and the top one is incompetent, say this is sandstone and say this is mica rich rock. Okay. Now, initially I have the same circle I have drawn here, and I am applying the same deformation here, and if we deform it, both of them would get sheared. However, because mica rich rocks are rheologically weaker, this ellipse of the deformed area would not be, this ellipse here would not be as systematic as we have drawn here, because this would deform more, this ellipse would be like this, and here it would deform less. So, we will get a local variation of the strain ellipse due to rheological contrast. So, clearly here the long axis is like this, and here the long axis is like this, and this is the reason of your cleavage diffraction. So, in incompetent layers or layers like mica rich layers, the angle is less, and in strong or competent layers this angle is high. Let us have a look on some examples. What we see here, I made a sketch on the other side, but you can clearly figure out that this is your primary foliation layer, and what is overall coming from this side to this side is your secondary foliation. That is the general trend, this dashed line I have drawn. But if we look closely here, as I have drawn here, that at this area these cleavages are a little bit deflected. Again these are coming at low angle here, here these are at high angle, and again here they are going at low angle. So, it appears like it is refracted, and therefore, this is known as cleavage refraction, and from this image we can figure out that this has more mica and this has more mica than this area, and I was in the field. So, I know this was mostly sand rich layer and this was mica rich layer. So, this is a classic example of the cleavage refraction. Now, if this cleavage refraction do happen systematically in a folded layer, then it gives a fantastic pattern which is known as cleavage fanning. Now, what happens? You see that this is the fold. So, here I would have a pattern like this, the low angles here. On the other side I would have pattern like this. So, overall the foliations would try to diverge away from the core. On the other hand, in the competent layers they would try to converge towards the core, and this makes a fantastic wavy pattern all over the fold. Of course, you have to see the entire fold, and this is known as cleavage fanning, and this happens due to cleavage refraction. So, in cleavage refraction, axial plane foliations typically fan, that is, they display a radiating pattern within the fold. The fan could be convergent or divergent depending on whether the foliation converges towards the core or towards the convex side of the fold respectively. Now, competent layers tend to develop parallel folds in which strain axes are high angles to the layer of boundaries, thereby generating convergent fans. The incompetent layers on the other hand tend to develop congruent folds which with large amounts of shear imposed by adjacent competent layers and consequently fostering divergent fans. Now, a series of terminologies are here like parallel folds, then congruent folds and so on. We will learn about it later, but I believe you understood the mechanism. If the layers are strong layers, that means competent layers, the foliations would converge towards the core, and if the layer is incompetent layer or weaker layer, the foliations would diverge away from the core. So, here is a cartoon diagram, but we will see the real field photographs in this slide. The first one is a field photograph. As you can see that this is your competent layer, or all these alternating layers are your competent layers. Here you can clearly see the foliations not that much developed, but you can figure out they are converging towards the core. Even here, if I try to figure out the trace of the foliations, at least in this section, is something like that, and I can figure out these are converging towards the core. However, if I try to look at this incompetent layer, which is this one, this area, it got a little bit eroded, but I clearly can identify that these are diverging away from the fold core, and therefore, these are your perfect example of cleavage fanning, where in the convergent layers, in competent layers they are converging towards the core, in the incompetent layers they are diverging away from the core. This is also a very classic example of thin sections, a photograph of a thin section, the photograph from John Ramsay. You can see this pinkish layer is a quartz rich layer, and this is of course a strong layer compared to this micaceous layer outside, the greenish one. You can clearly see that if this I consider this is the fold core, the layers are diverging away, and this is absolutely what is known as cleavage or foliation fanning. Now, cleavage transaction is something different. So, what happens, you have formed the fold, you form the axial planar cleavage, but the fold is continuously rotating due to shearing or some sort of oblique deformation. So, therefore, the axial planes or axial planar cleavage would also tend to rotate, and they not necessarily track the axial plane of this fold. So, in this illustration, if you see that this is actually your axial plane, or this is the actual axial plane. However, this foliation is drawn by this blue shade plane is not tracking the axial plane, it is slightly deviated, and this is known as cleavage transaction. So, transaction is generally attributed to a rotating strain field during folding, with eventually pre-folding initiation of foliation and fold axis developing oblique to the bulk flattening direction. Now, we more or less have covered the basic terminologies related to foliation. What is left is the mechanism or formation of foliations. How do they form? We will not go into the detail of this part, but I just give you some examples. So, I just give you some examples. So, there are 4 major micromechanisms responsible for the development of the foliation in deformed rocks, and these 4 major mechanisms, they can work separately or in conjugation. The first one is shape controlled mechanical rotation of pre-existing inequant grains or fabrics. The second one is modification of grain shape and volume through pressure solution. The third one is modification of grain shape by intracrystal slip or diffusion. If you remember that the slip systems or diffusion creeps, they produce some sort of shape preferred or crystal preferred orientation. This is what exactly we are talking about. And the fourth and final one is the growth of inequant grains in preferred dimensional orientation under the deviatic stress field. So, all these 4 mechanisms are actually summarized by a fantastic summary diagram by Pasquier and Trau in their 2005 book of microtectonics. So, here there are many textures or many features, geological features, which got deformed this way, compressed this way and got extended this way, and you can see they all of them are showing some sort of fabric development along this direction. You can look at this image in detail. So, for example, here you have elongated grains which were initially spherical, you have some sort of pressure shadows, we have grain uniaxial unidirectional grain growth here. So, multiple crystals, a single crystal came, you have unidirectional grain growth. So, you have a nucleus here, and then because of this compression the grain is growing mostly in this direction and so on. So, this is a fantastic summary diagram defining or describing the formation mechanisms of foliations in deformed rocks. So, I conclude this lecture here on foliation, and in the next lecture we will discuss the linear feature of deformed rocks. In other ways, we will talk about lineation. Thank you very much. See you in the next lecture.